Hello, Honors Math 2. As we continue through Honors Math 3, Module 1, we refresh our memory on exponential functions. Let's look at the graph of an exponential function. First of all, imagine the difference between this function f of x and this function g of x. Imagine what those two graphs would look like. You should recognize that this function is quadratic, and the shape of a quadratic function looks like this. You should recognize that this function, g of x, that's an exponential function. By exponential, we mean the variable exponential. The variable is in the exponent. So this is an exponential function, but this is quadratic. Once you imagine this function, you should also realize that if it's quadratic, this function is not a one-to-one function. That means the inverse will not be a function. But this function, if you can remember the general shape of an exponential function, this is a one-to-one function, and its inverse will be a function. Okay, so I'm going to graph this parabola shifted up 4 units, but I'm going to limit the domain so that the inverse will be a function. If you remember what that function looks like, I'm going to go up 4, put a point, over 1, up 1, over 2, up 1, 2, 3, 4. But if I go the other way, that will not be a one-to-one function, so I'm just going to keep the right-hand side of that parabola. And that's my function f of x with a limited domain from 0 to infinity, so that the inverse will be a function. Please notice the range of that function and jot it down. The range of that function starts at 4 and goes forever up. So the range is from 4 to infinity. All right? If that's my function f of x, I'm going to change that to y equals x squared plus 4. And I'm going to ask you to find the function for the inverse. I'll pause while you find the equation of that inverse function. Okay, to find f inverse, I switch the x and y. I solve for y. When I take the square root, I get y equals the plus or minus the square root of x minus 4. That would make something that, this is not a function if I take plus or minus, so I'm only going to take half of it, and my inverse becomes f inverse of x. I'm going to take the top half, square root of x minus 4. All right, so that's my inverse function, square root function. Notice I can only put positive numbers under the square root. That means that x minus 4 has to be greater than or equal to 0. And that implies that x is greater than or equal to 4, which is kind of nice because that confirms my domain is from 4 to infinity, which was actually the range of that original function. Alrighty, let me sketch the square root function, which shifts to the right 4. 1, 2, 3, 4. Up 1 over 1, up 2 over 1, 2, 3, 4, and there's that hook to the right, and that is f inverse of x. Alrighty, please notice the range. Awesome. The range, the y values start at 0 and go forever up, which confirms that the domain of the original is actually the range of the inverse. Alrighty, so again, this is just a quadratic function, it's not exponential. Let's refresh our memory on an exponential function. I usually suggest this, x, g of x. For my few key points for an exponential function, I'm going to plug in 1, 0, negative 1. Please find those outputs and notice the domain and the range of this function. I'll pause. Plug in 1, 2 to the first is 2, 2 to the 0 is 1. Any number to the 0 power is 1. 2 to the negative 1, remember that negative exponent moves that 2 down, and I get 1/2. When I plot the points 1, 2, 0, 1, negative 1, 1/2, here's the graph of my exponential function. I'm just switching colors so you can tell the difference between f of x and g of x. Alrighty, look at the domain. Please state the domain and range of that green function. I can plug anything into that function, so my domain is all real numbers, negative infinity to infinity, but notice the range, I'm only getting numbers from 0 and up, 0 to infinity. I never touched that line, so remember that I get an asymptote for an exponential function. Is that an x equals or a y equals, that asymptote? Notice that's a y is equal to 0. If I asked you to find the inverse of this function, g inverse, you would rewrite that as y is equal to 2 to the x. You would switch the x and y and solve for y. I'll pause. All right, I don't know if you noticed, but it's impossible to get that y out of that exponent. To solve for y, it's impossible to do that with what you know so far. Haha, stay tuned. We're going to see this soon. Alrighty, so right now I'm just going to switch those ordered pairs. So if this is the inverse of g of x, that means all elements of the range up above becomes the domain. All elements of the domain become the range. Please plot those ordered pairs and connect them. I'm going to use green again. When I reverse the ordered pairs and plot them, there is my g inverse, and you can see that symmetry over the line y equals x. Notice the asymptote for this new inverse function. Now I have a vertical asymptote, and a vertical asymptote is always an x equals. Alrighty. You can state the domain and range also. That would be helpful. I'll pause while you state the domain and range of that inverse function. Notice now my domain starts at 0 and goes to the right, but my range includes all real numbers from negative infinity to infinity. Please take some time on your own and read through some properties of some exponential functions that you remember. And then I'm going to ask you to pause the video and graph this thing. F of x, x, f of x. Get some ordered pairs on that graph. Plot that graph, and then we'll sketch the inverse. Alrighty, I'll pause while you do that. Okay, another nice exponential function, but I don't know if you remember when the base is less than 1. When that base is less than 1, I actually get exponential decay. That's why it's decreasing from left to right. Check your ordered pairs. I always put parentheses because those parentheses mean you have to raise the numerator and the denominator to the negative power. My outputs become 1/2, 1, and 2. There's my graph. To graph the inverse, I reverse those ordered pairs. And I'm going to pause and plot these points on the inverse. There's my graph of f inverse when I reverse the domain and range. And would you look at that? We have that symmetry across the line y equals x. All right, very nice. I'm going to ask you, just as a good review of some exponential functions, imagine what this graph would look like. I would probably imagine some key points on this graph, x, y. When I plug in 1, 0, -1, what would that look like? And then I'm going to sketch this just using transformations. What does subtracting 3 do to that function? And what does that do to those ordered pairs then if I subtract 3? Or for g of x, x, g of x, what would subtracting 5 inside do to that graph or do to those ordered pairs? All right, what would those ordered pairs be first? I'm not going to graph it. I'm just going to use those to graph these. Okay, sometimes I call that my parent function. Y equals 2 to the x is my parent function. And using these key points that we had before, think about what subtracting 3 does to that parent function. Subtracting 3 moves that whole function down 3. So my inputs don't change at all. But if I move that whole graph down 3, those outputs, I'm going to subtract 3. So 2 minus 3 is -1. 1 minus 3 is -2. 1/2 minus 3 is -2.5. And plot those points. I'm going to pause. For my exponential function, there's my ordered pairs. Now imagine if I take that parent function, which did have an asymptote at y equals 0, and I shift it down 3, that asymptote becomes y equals -3. So I kind of like to sketch that asymptote and then connect those points. Alrighty. And there's a nice little exponential function shifted down 3, and that's my graph of f of x. What would g of x look like? Think about what that subtracting 5 inside that function does to that parent function. I'll pause while you think for a minute. When I subtract 5 from the x's, that's affecting my inputs. My inputs are x values and move left and right, actually opposite of what you expect. So that's a shift right 5 of that parent function. If I shift to the right, that affects my x coordinates. So I'm going to shift all of these x coordinates to the right 5. 1 plus 5, 0 plus 5, -1 plus 5, and my y values, my outputs will not change. Okay, pause and connect those ordered pairs. I'm going to change colors. For g of x, please notice I just took my parent function, shifted it to the right 5 does not change my asymptote, so that still has an asymptote of y equals 0. Alrighty, so it's a little review of graphing exponential functions. There's a method to our madness, why we're reviewing exponential functions for what comes next. Alrighty, but before we do, here's a quick review of some properties of exponents. And while we're talking exponential functions, let's solve a couple exponential equations. Remember, when the bases are the same, we add the exponents. When I raise a power to a power, I multiply those exponents. When I raise a product to a power, I have to raise everything inside to that same power. 1 to any power is 1. Any number to the 0 power is 1. And when I have a negative exponent, that becomes 1 over that base to that exponent. It's a reciprocal, we call it. If you were asked to solve 3 to the x plus 1 equals 81, it's a tough equation to solve. So I'm always going to try to rewrite both sides with the same base. This is 3 to the x plus 1. I can rewrite 81 as 3 to a power. 3 to what power is 81? 3 times 3 is 9, times 3 is 27, times 3 is 81, so 81 is 3 to the 4th. Once the bases are the same, the exponents have to be the same, so x plus 1 has to equal 4, and x must equal 3. Alright, so good practice to solve some exponential equations. I need to get these bases the same on the left and the right. Can you think of a number to a power that gives you 4? Same number to a power that gives you 8? I'll pause. In this case, my base is going to be 2, because I know 2 to a power is 4. That's 2 squared, and I'm going to raise that to the 2x minus 1. And 2 to the 3rd is 8, so that's my 2 to the 3rd, but now I have to raise that to the x plus 3. Go back to my properties up here. When I raise a power to a power, I multiply, so I'm going to multiply these. That's 2 to the distribute. What is that? 4x minus 2 is equal to, distribute over here when I multiply, 2 to the 3x plus 9. So that means that once the bases are the same, the exponents have to be equal, and 4x, what is that? 4x minus 2 has to equal 3x plus 9. And solve that equation for x. And we get x is equal to 11. Look at that next case in part C. You can see the base, 4 is 2 to a number, 1/2 is 2 to a power. So rewrite 4 with a base of 2 and rewrite 1/2 with a base of 2. Think about that for 1 second. A little trickier with that fraction. So here, 4 is 2 squared, and then I have to raise that to the x power. 1/2 is, bring it up, 2 to the negative 1, and I have to raise that to the x minus 3 power. Power to a power I multiply, 2 to the 2x is equal to, power to a power I multiply, negative x plus 3. So solve that little equation, 2x is equal to negative x plus 3. And I get that x is equal to 1. You can always plug it back in and see if it works. Alright, rewrite 9 with the same base as rewriting 27 as a number, some base to a power, some base to a power, and then I have to raise that to the 2x, and I have to raise that to the x minus 1. Alright, rewrite 9 and 27 with the same base. I can rewrite both of those with a base of 3. 9 is 3 squared, 27 is 3 to the 3rd, multiply becomes 3 to the 4x, is equal to 3 to the 3x minus 3. And once the bases are the same, you can set the exponents equal to each other. 4x is equal to 3x minus 3, and x must equal negative 3. Alrighty, thanks for trying homework day 5. There's a little bit of tricky factoring on some of the homework with some of those exponents. Just so you know, after this module, we're going to do a little algebra review of some factoring and some good things. So thanks for trying some homework and checking your solutions. Have a great day. Thanks for watching.